So the quarter is almost over. And now we are ready to introduce the main ingredient of this seminar, so-called the EM algorithm that Samuel will investigate next quarter especially. So today I'd like to give you the intuition about the so-called the EM algorithm. But what we should know is that I intentionally write down this with the small letters because this is different from so-called the capital letter EM algorithm, okay? So today, let me try to explain this really intuitively, and I'd like to justify why so far we have sort of focused on calculating the sectional curvature or the Gaussian curvature in order to understand some stupid algorithm in the applied world. So why that was really necessary. Let me try to explain that somehow nicely. So the most important background is coming from the linear algebra. So as long as you care the mathematics towards the applied direction, the most important term in my personal opinion is so-called the, can you guess what this letter H stands for? This H stands for the
semi-space.
The Hilbert space. Okay. So I bet this would be the most important term towards the applied direction in terms of the mathematics. So this means, mathematically speaking, this is nothing but the vector space, okay? So first of all, this is a vector space. Okay, and let's just assume in order to consider the vector space, then we should get the scalar multiplication. So let's just assume the scalar is coming from just a real field, okay? So we can take the complex field, for example, but for our application, let's just focus on just a real world. It keep with 1. So far we have talked about the geometry, so that we'd like to quantify the geometrically meaningful quantities, so that we should equate with the inner product. Is it clear? So that we'd like to equate with certain inner product on the given vector space, but as long as we'd like to say this space is the so-called Hilbert space, so this already has the name so-called the inner product space, but we had a special name on it, so satisfying so-called the completeness. This is the definition. So if I just write down this in just one word, so this is usually written as a complete inner product space. This is the another name of the Hilbert space. And I bet, excuse me. So as long as you care towards the applied direction, whatever applications that you care, the most significant and important term, mathematically speaking, would be this kind, the Hilbert space. And let me try to explain why this is somehow most significant, like the object. So there's an applied professor. So do you agree that the Hilbert space would be one of the most important term in the applied world?
Of course.
Yeah, of course, right? This definitely that should be the case. No doubt. Okay. So let me try to explain, especially the meaning of the completeness here. So according to the linear algebra, so given an inner product space, let me just say just given inner product. So what's the inner product? This is the function. You agree? So it takes basically two vectors. So this is as a function takes h cross h. Got it? It takes two vectors from each vector spaces, and let's just say it assigns to a certain real value, right? So that we should be able to define for each vector from this vector space, okay? For each element from here, so we should be able to define the notion of the magnitude. Do you agree? So how did we define this? So we simply just plug in. So this notation just means that we would like to define the notion of the magnitude of each v in terms of chosen inner product, right? We'd like to put this into the same, like the vector v inside of the first and the second slot here, and then we will simply put this square root. Are you familiar with this? So, and we just define this we clarify the magnitude of the v. So what? So now we have the notion of the magnitude. Then we'd like to also define the notion of the distance. So in order to simplify the notation, so let me just write the notation distance by just d, sub this Hilbert space H. Okay, so I already specify a certain inner product. Got it? So I'd like to measure the distance between x and y on the given vector space, so that as long as you have the vector x and y, then what can you do? We should be able to define the notion of the x minus y. Do you agree? Then we should be able to define this in terms of the magnitude of x minus y. Is it clear? So the basic logic is that as long as you have the inner product, then you should be able to define the notion of the magnitude that gives the notion of the distance. Is it clear? Of course, converse might not hold in general, but as long as you have the inner product, that induces the notion of the norm, it induces the notion of the distance. Is it clear? And we'll say this d sub h is complete if, so naively speaking, there is no hole in H. So equivalently, our Cauchy sequence is convergent. This is a rigorous term, how to define the notion of the hole. So let me just give you the non-example. So let's just simply take the set of the rational numbers. Got it? So are you familiar with this notation? So just Q means the all possible rational numbers in the inside of the real line. So let me just draw indeed just naively the set of the rational numbers. So if you just take R subtract by this Q, then there are lots of holes. In this case, this is incomplete. So that you should be able to find lots of holes.
So in the real analysis course, we call this density?
Yeah, density. So this is the dense subset, of course, but this dense subset is definitely different from the ambient space arrow here, right? So that as long as we can fill all possible like the holes here, then we'll say such a like the space is complete. So no hole, basically. Okay? So I so far just said blah blah blah. That's just nothing but the notion of the Hilbert space. But we need to justify why we need to care this notion, right? So the most important reason, the question why one cares the Hilbert space. And I bet this question would be the most important question for the applied world. So just try. So what do you guess? Why people actually care this one? Indeed, there are, I should say, tons of applications from the Hilbert space, okay? Indeed, tons. So as long as something becomes non-trivial in your application, it should be related to a Hilbert space, basically speaking. So that
You can, any kind of space like the vector spaces we're used to can be, no, I take that back.
yeah, it might work. So, and even try. So why people care the notion of the Hilbert space?
It's something to do with, you can apply analysis techniques like limits, different.
That's quite fancy. So you might even heard about the reason when you were in the kindergarten, to be honest. Why we need to care? There's a one single theorem you might heard more than 100,000 times about certain theorem. It's related to the right triangle. You might give it a hint. Pythagorean theorem. Answer. And And the notion of the Pythagorean theorem in the context of the statistical model we will call it by this EM algorithm. So that after spending next quarter, just some of like the non-experts ask you, what is the EM algorithm you have worked on? Then you can say it's just nothing but the Pythagorean theorem of the statistical models. Okay, but let me try to explain why this is significant. So the following is the familiar form of the Pythagorean theorem. And in order to describe it, so the vector space equipped with the inner product is not sufficient. If you try to track the proof of it, of this theorem, so you should require the notion of the completeness. So that's why we need to consider the Hilbert space, because we actually want to care this one. So given a Hilbert space, okay, so let's just write as fancy as possible. So let's just try the fancy drawing. So this is my vector y. Okay, so let me just fix any x and y. Okay, those are just elements inside of the given vector space, so that you can just identify, diagonally identify those as just two arrows, basically speaking. But let me just consider non-zero vectors. Okay, well the zero vector is just not interesting. That's the reason. So that one vector, let me just write down in this manner, just draw it in this manner. And another one, for example, this is my y, and this is my x. Is it clear? I just try to draw it in the diagonally. So as long as we have the inner product, so if you remind your knowledge from S6A, for example, you knew the notion of the orthogonal projection. Have you remembered that? So what we learned before is we should be able to take this projection here. Got it? And you are able to actually write down this also explicit. So the direction should be just the same as the direction of the y. So let me just write down this just by y. But what you need to multiply by is x with y divided by y of y. Then you will get this vector. This is just the same. So start from the vector x, and once you take the project down to the direction of the y, the corresponding vector would be just this form. It's not difficult to prove it, okay? So now we are still working everything inside of the certain vector space, so that what you can do is you should be able to find this direction. How? Because you already know those two. What is the corresponding subtraction? It's indeed just nothing but the subtraction. Agree? So that what you should get is this line, and this is definitely perpendicular. Is it clear? And if you want to just prove it, then you can just plug in those two into the inner product, and you can prove that should be equal to 0, meaning that two vectors are perpendicular. So at least that's what we assume. For the senior level, we already saw the linear algebra before. So what's the Pythagorean theorem then? As long as we care the magnitude of the hypotenuse, right? This should be exactly the same as 1. So 1 is this one. Another one is this one. You agree? So I will not give it a proof, but you should be able to prove it if you're curious, right? So just write down the definition of each terms, and just using the inner product, you should be able to prove it. You can just compare those two, and those two should be the same. So two things. Number one, intuitively this is clear. Is it clear? Intuitively clear. So why this is important? So let's try to look at the example. So what is the most significant example of the Hilbert space? It's definitely the finite dimensional Euclidean space. Okay, so the first example is just simply Rn. Rn is clearly the vector space. It equips with the vector addition with the scalar multiplication. Is clear? So we'd like to equip with the so-called dot product. So this would be today most important example in some sense. So indeed, once we take the vectors, say in Rn, so that you should be able to write down each component for x and y. Then what's the definition? It's just a dumb question. It's just this guy. But I will not satisfy this expression today. This is just clear as far as you already saw this tons of times. So the expression I prefer today, with certain purpose eventually, is that I'd like to write down the expression in this manner. Got it? And the between, what is the corresponding matrix here? This is just nothing but the identity matrix. Of course, clearly those are just the same, but the putting the dot product, which is a specific choice of the inner product, correspond to the identity matrix. So far so good? So this is the one of examples of the Hilbert space. Is it clear? So that is a complete inner product space. So now let's consider the statistical context at this point. So still, I'd like to consider the same set, since this n is any natural number. Okay, n is any natural number. So now let me just try to change the inner product, okay, from the dot product to the something else. So I'd like to specify the dependency for this inner product, so that let me just write down as a inner product sub p. So here p means the following. So here p, let me just mention as it is the vector in Rn, so that it consists of n components, basically speaking. So that I first fix the p from here, and I will require each p1 to pn, all components should be positive. This is my requirement. And furthermore, let me also require the summation of all of them is equal to 1. Okay? So now let's look at the statistical context. What's the object here? What is this p? This vector has a different name. This is what?
Distribution?
Is correct, but more specific. You can narrow down further this object. This is probability mass function. Okay?
Oh, yeah.
Got it? So that if you just draw some histogram, so that this is the one of the object of the probability mass function. Do you agree? So can you imagine why I write this object at this point? We're showing you the identity matrix. We'd like to replace the identity matrix by what? Just by this guy. Okay, so what we should do, you can actually see something happen already. So we define this guy. How? Up to here, everything is the same. But we will simply change the diagonal entries by each piece of y. Is it clear? So if you just remind the spectral theorem, that gives the symmetry matrix to be the diagonal matrix. So those quantities are so-called the eigenvalues. And I will just make my eigenvalues to be all positive. Is it clear? So that you can also check that this also becomes another inner product. And equipped with this type of the inner product, this also becomes a Hilbert space, even though the inner product is different from the previous example. So what can you see? So somehow the statistical context already enter that we'd like to see why this plays a role. So far, I intentionally didn't mention one thing. So what is this then? What is this then?
So what was the question?
What is this n? That's my question.
So arbitrary finite dimension?
Arbitrarily natural number, that's what you assume, right? So indeed, let me just write down this expression again. So this becomes the summation from 1 to n of xi multiplied by yi multiplied by pi. You agree? So, or if you want to write down more stochastic manner, so this is just the expectation of x plus y, to be honest. Whatever. Right? So that whereas from some context you view this with the linear algebra with the eigenvalues, some context you look at some stochastic context, so it's actually just the same. So Number 3. Question is the following. Can we make n to be infinity? Here, you assume n is finite. You agree? Here, you assume n is finite. That yields the finite summation, so that we do not need to worry about the well-definedness or the convergence at all. So this is just finite summation. What if we make n to be infinity? Is it possible?
You take the limit?
Yeah, that's my question. Can we take the limit
Of that summation?
with respect to this n?
Yeah.
Right? Is it possible? What should be the answer? Why not? Yeah, why not, right? That's why we learn the limit. So that's what the calculus is for, right? So as long as this expression holds for each n, then why not we
Oh, I see.
take the
You wanna
limit?
you want to talk about continuous distribution, like a PDF.
Almost close, but not exactly yet. So now let's take n to be infinity. So the corresponding vector space now becomes this guy, right? So if you write down the corresponding inner product here, what happened? So if you write down also the same expression, the only difference would be what? So that you just need to make this to be infinity. So now you just need to put the additional assumption that this series is convergent, right? As long as you have that assumption, then there should be no issue. Do you agree? Naively speaking. So, but let's just now at this point write down this more clearly, because this is also one of the most important objects in the analysis. So behind the notion of the so-called small r2. So this space is the following. So if you look at this guy, this expression. So this expression only makes sense as long as you put x and y consist of infinite many components. You agree? In order to make this expression rigorously correct, our possible way to interpret this mathematically correctly is that there should be infinite many components. Do you agree? But this is not rigorously defined. So that we are not preferring to write down the vector expression in this manner, because this is not clear. So that you should be able to replace the expression by what? X is indeed the function from the natural number to the real. Why? So for each natural number, you just have the corresponding component, right? For each choices. So rather than using the vector expression, in the case of the infinite many components, you can view each x and y as a function from n to r. And you will call such a function the sequence. This is the definition of the sequence. And also same for y. Is it clear? So now we do not need to care how many elements inside of this n, right? Even though the set n contains infinite many elements, we do not care. For each natural number, we have just corresponding real number. That's what this notation really means. Do you agree? And we'd like to identify each element here as a vector. So the corresponding space, usually people write down this with n here, but notation is not over here. So that we collect all possible what? Functions. This should be viewed as a vector, which is a generalization of the finite many components.
Wait,
Mhm.
isn't that like a linear functional?
This is not the linear function. So all we know is that each vectors consists of n infinite many elements, but each natural number indices, you have some real number. Do you agree? So there is a x1, x2, x3, and so on and so on. So that we can just replace the notation by just looking at the function from natural number to the set of the reals. So for each nth component, we just have the
So
corresponding
you
real
map,
number.
You map every single natural number.
Every single natural number. So there's a corresponding assigned real number. That's the meaning of the nth component here.
What, I mean,
Yeah.
why not just pick the identity map for everything?
So for example, if you choose n to be equal to 3, okay? So that if you choose the vector as say 1 to 3, in R3. So then you can just view this as a function from the set consists of, this notation is really bad, so let me just use ABC, for example. So that you can just assign this to the set of the real. So 1 corresponds to A, 2 corresponds to B, 3 corresponds to C. So that those two are actually just the same. It's just we change the way of the represent the same object. But as long as you have the infinite many components, this notation doesn't make sense any longer, because this is not mathematically verified. Whereas in the case of the finite many components, this is definitely the good way to represent the vector. But for this case, it isn't any longer. We do not want to write down this manner. But we can still use this type of the so-called functional representative. Then for each component, you know how to assign the real number. This function represents the vector x. It's just a way to abstractize the same object in the case of the vector with infinite many components. So this is just a function such that this notation should make sense. So that we will just make require the convergent condition. This has a name. This is a so-called a small L2 space. I highly recommend you to know the name, because time to time this is really used a lot in the applied world, right, Professor Park? Do you agree? This is also one of the important vector space. Yeah, this is quite important. Okay. So at this point, you can see why the notion of the Hilbert space is significant. Number one, we have the notion of the Pythagorean theorem that even holds for the infinite dimensional space. So you cannot indeed visualize rigorously, but we know how to make the mathematical analog from the visualization of the dimension 2 or 3. That even holds for the infinite dimensional case. That is something, right? Because those are just the examples that support this theorem. Is it clear so far? So at this point, let me just ask you one thing. So what? So still, why this theorem is indeed significant? Why we need to care? So one of the reasons, there are tons of reasons for sure, but one of the reasons I bet is that you can now appreciate certain picture that just this is one remark that you have used thousands of times. So what did I draw here? So for example, let me just draw the case of the Hilbert space, same as just the three-dimensional Euclidean space. Okay? Then you are super familiar with just drawing the x, y, z axis. Agree? You're so familiar with it. So let me just put the different colors. With the white, purple, and green. Like this. Let me ask you at this point, rigorously, why this picture makes sense? Why? First of all, you already make perpendicular to each axis, so that you already make the 90-degree difference compared to different axes. This only makes sense when you apply this type of theorem. Because you have the Pythagorean theorem, you can so-called decompose the space into the smaller subspaces, right? So by Pythagorean theorem, we are able to decompose H into smaller subspaces. So that as long as you know one vector, then you know we can just decompose this vector V consists of X component, Y component, Z component. This expression only makes sense as long as we have the Pythagorean theorem. So that we already know how to decompose the space very nicely. So far, so good?
Sorry, so like we're already in R3, so what do you mean by decompose them?
So as long as we do not know how to draw the three axes in this manner, then we are not able to represent the vector in this manner, right? So as long as you already write down the vector as a times 1, 0, 0 plus b times 0, 1, 0 plus c times 0, 0, 1, that just means that you already know how to decompose this vector somehow nicely, right? Because this component is nothing to do with the other directions. So this expression only makes sense as long as we have the Pythagorean theorem. Because this theorem gives the way to decompose in the perpendicular like a fashion. Sammy, can you open the door?
Think someone blocked it.
Correct it? Someone wants us to study forever. Yeah. So that's why. So that based on the theorem, so we should be able to decompose the space somehow very nicely, and we just need to investigate each smaller subspaces. So there are tons of applications, including the Ries representative theorem and so on and so on. But so here is now our time to look at the EM algorithm. So why I didn't mention this somehow really important mathematical ingredients from the beginning? Why almost the end of the quarter, now I begin to mention this important like the ingredients? Why is that? So the reason should be the following. So just give me one statistical models, for example, like the Neumann distribution. Okay, so one crucial fact. Statistical models are not Hilbert space. So in order to decompose the space nicely, then you should start from the Hilbert space structure. So let me just give you the simplest example. So what's the example? So just a space, it's a set of what? One-dimensional Neumann distribution. So we somehow put lots of effort to understand this object geometrically speaking. So what do we know? So when we choose any point from the upper plane, you agree? So that as long as we choose any mu with the sigma, then if I just write down this by so-called parameter in the terminology of statistics by theta, then it just determines one of the just value with the mean given by just mu and the standard deviation given by sigma. And the function looks like the Gaussian loss order. You agree? So if you look at this set, is this set the vector space? Cannot be, right? Because the scalar multiplication is not well defined, right? You cannot multiply by the negative number, for example. So this set never can be the vector space. You agree? So the Hilbert space already requires the vector space structure. It requires the vector addition and the scalar multiplication, both of them. So such a like the upper plane is never a Hilbert space. So far so good? Do you agree? So let me just tell you again. So in order to use the last of the important theorem from the Hilbert space structure, indeed we need to require the Hilbert space structure, right? That's so clear. But even in this most simplest example, this is not even the vector space. So that the very first like the assumption is broken down completely. So that you cannot use anything regarding the Hilbert space structure. Is it clear? And most of the cases, the statistical models are never actually the vector space. So that's the starting point of the learning the geometry of the statistical models. The very first point is that this is never vector space. So that this is never the Hilbert space. So that you cannot use any like the good properties of the Hilbert space. Then what can you do? So then what's the question? Do we still have the Pythagorean theorem. For statistical models. This doesn't make sense in the viewpoint from the Hilbert space structure, because the Pythagorean theorem is one of the special property of the Hilbert space. But even in this simplest example of the statistical models, this is never a vector space. So the question is then, can we still replace that theorem in the context of statistical models? That's what we call it by the EM algorithm. Let me now address this part. So let me just spend just this slide, this side, to just represent the main theorem today I want to just share. So this is indeed the Pythagorean theorem. Proven by Amari. I bet it's around the 82. So it's somehow very classic. So S is the set of probability distributions. Let me just say probability density functions. Okay, so as you see from this example, this is never Hilbert space. You can easily verify from this example. Agree? So that let me just draw this set indeed naively. Just a picture. Already, this set S is never the Hilbert space, as I said. So let me just choose 3 elements from here, say P, say Q, say R. That satisfies sort of a Pythagorean relation. So suppose we already have, there exists PQR from S. And I want to draw such a picture with comparing this situation. So in order to talk about the norm square, this doesn't make sense because the notion of the norm is only defined in terms of the vector space, whereas this is never the vector space in general. So it doesn't make sense. So can you guess how to replace the notion of the either the distance square or the norm square? We already saw it last time. What's the notion? Tail divergence, such that. So I'd like to measure the distance between P and R. So let me remind you what was the tail divergence if you don't remember it. This indeed replaced the notion of the distance square. So the distance between P and R, distance square, is the same as the distance square between P and Q plus Q and R. So this is just the assumption, not end of the theorem. So what I assume here is that I have the Pythagorean theorem. Suppose that I already have 3 probability densities, okay, satisfying the relation of the Pythagorean theorem. I just assume that's the case. So what happened is the following. And you might wonder, so why we have spent all of our time to just calculate the sectional curvature? It's nothing to do with this type of the applied work. So why that should be matter? So then this happens. Then what we will do is that we'd like to connect them, and the notation really matters. So let me intentionally write down this part by using the notion M. Here M is so-called the mixture family. That if necessary, I will define it. So, and for this part, let me use the notation, say, E. Here E means the exponential family. okay? Whatever that is. So that let me just use this one. And here, I'd like to parameterize this in terms of t, use here s by s, then with p times tm and r times se. So this would be defined as just a t times p plus 1 minus t times q. And this guy is defined as a q times s times r times 1 minus s with the some normalization constant. Okay, meaning that the total integration of this guy is equal to 1, and this the constant is adjust this to be just a product density function. Then what you will get is that KL between those two, you will get this one. This is a theorem. So let me write down. So PTM and this Q is equal to KL of the Q, this guy, so this is R sub S. This guy is equal to KL between this one and this one, plus this one and this one. This is a theorem that Sammy will investigate next quarter. So today, let me just try to interpret what this theorem really means. And what I want you to imagine is how to generalize the notion of the Pythagorean theorem in the case of the Hilbert space into the case of the non-vector spaces in general. So let me first give you some intuition, what was really going on. So let me just give you the ingredients. So if you look at the third lecture, you can visit my website and just view my lecture note. So what we saw is the notion of the distance square is somehow similar to the KL divergence. Okay, so let's just at this point just simply accept we should be able to replace the distance square by using the notion of the KL divergence. So KL divergence, let me just remind you. So the definition is not really helpful for the intuition for the beginners. So that this is written as a log of px divided by qx times qx dx. This is the definition. In the case of the product mass function, you just need to replace the integration by just a finite summation whatsoever. But this is just some messy definition of the KL divergence, and if you just review the third lecture note, then you kind of understand why we should be able to replace the notion of the distance square, which is here, distance square, by using the KL divergence. So if you want to justify it, just read it, okay, the third lecture note. So now let's just appreciate this theorem. So the starting point is that we already start from the relation of the Pythagorean theorem. This is sort of the right triangle. Mathematically, this doesn't make sense because we are not working on the ambient space, which is the flat like a vector space, but sort of the similar. So that you might wonder, so how can we make this notion of the 90-degree totally make sense? So can you guess? In order to talk about the notion of the angle, we need to introduce the notion of the inner product, or the Riemannian metric, or the first fundamental form. What is the Riemannian metric, or the first fundamental form here? What should be the notion? In order to make this notation 90 degree here to be mathematically correct, then you need to specify the inner product at point Q in order to talk about the 90 degree. You agree? Then we should specify the choice of the inner product on this tangent space. What is this inner product? So far you have just learned only single sentence of the Riemannian metric from this seminar. What's its name? This is visual information metric. Okay. And for the advanced like the learner, so the notion of the efficient information is just the same as the inner product of L2 space. This is just the same, to be honest. So that this is just a natural replacement from the L2 space, which is Hilbert space, to the just the corresponding inner product on the tangent space. Then still you might ask, so what? So why this theorem totally makes sense? So in the case of the Hilbert space, as I said, for example, we are able to decompose the space in terms of the x, y, and z axis. So, but the ambient space there is any longer the vector space. So now let's just look at the geometric intuition. So this is today all I want to say. So geometrically speaking, in terms of the Gaussian curvature, what's the feature of the Euclidean space? The Gaussian curvature of the Euclidean space should be equal to what?
0.
0. You agree? That's the way to characterize the Euclidean space. So we'd like to say the given space is the Euclidean space if and only if.
So every ambient space needs to have Gaussian curvature of 0.
As long as so we start from the ambient space, and ambient space is just nothing but the Euclidean space if and only if the sectional curvature or the Gaussian curvature, which are the equivalent word, should be equal to 0. Got it? Just as a fact. But in this case, this is never equal to 0 for the ambient space because we know that the ambient space is never the Hilbert space. Is it clear? But still, we'd like to decompose in this manner. So still, each one-dimensional subspaces here is still the sort of the Euclidean spaces. You agree? So the Gaussian curvature of each subspaces should be equal to 0. So what do you guess? So can you guess the subspaces here, or the statistical submodels here, has Gaussian curvature or sectional curvature equal to what? Should be 0. Okay, so that's why this theorem is special. So behind, now you can see the reason behind. So this trajectory has a special name. So this guy is usually called by the so-called the M geodesic. And this guy is called by the E geodesic. And this trajectory here is same as the so-called mixture family, and this trajectory corresponds to the exponential family. So what do you expect? So those exponential family and mixture family. And if you took the statistical classes before, so you might heard about certain names of the Poisson distribution, for example, like the Poisson distribution, Cauchy distribution, lots of them. Most of them are just the exponential family, okay? And the mixture family is also like just a natural like the so selection of the discrete property mass functions. So they have this is just value. What? They have 0 sectional curvatures. So they will call, but here I actually summed like only some things that you actually eventually I will need to explain and you need to learn. So called the dually flat manifold related to the one pair of the connections. If you look at the reference paper. So here's the idea. So we'd like to decompose the statistical models somehow in the nice fashion. But this doesn't make sense in terms of the Hilbert space. But what we can still do is that, so rather than just looking at the ambient space, if we look at the subspaces, as long as we can make the curvature equal to 0, then still we can describe the nice decomposition in terms of the KL divergence, that's nothing but the distance squared. So that as long as you can find the statistical submodels correspond to the curvature equal to 0, then you should be also able to write down the Pythagorean theorem. Then what can you do? So the EM algorithm just means that you can just go from here to here and go from here to here. That just corresponds to the point from here to here. And you can just repeat this. This is usually called by the EM algorithm.
So you're saying that the relationship between those geodesics obeys the Pythagorean theorem?
Yeah, this theorem is, so the statement here is so-called the Pythagorean theorem. And based on the theorem, okay, based on the theorem, so what EM algorithm is doing is that we will just repeat from here. So once you just reach here, then we will take this point by just taking so-called the N geodesic. And then once we reach here, then we will move from here to here by taking the E geodesic. And once you reach here, then you can take the further M geodesic. Then you can just repeat this procedure. This is we usually call by the EM
So
algorithm.
this is within the space of any arbitrary valid probability distributions under the Fisher information metric.
That's a really good point. So two things. Number one, as you said, this Pythagorean theorem works for any set of the probability distributions. Okay? This works for any ambient space. Consists of the certain PDF or PMF, we do not care. But if you choose the specific set of the PDF or PMF, it has a special feature. So some of the set as the the performance of this algorithm is not really good. But certain choices like the exponential family or the mixture family, this algorithm works really well, and also geometric interpretations. But the algorithm is just taking the minimization of the KI divergence just repeatedly. However, now you have certain geometric understanding. So now you see, so let me just finish today's the seminar by just saying one word. So this is the geometric foundation to replace the situation of the Hilbert space to the situation of the manifold. So I so far just intentionally just didn't mention all this theorem because actually eventually we will not care the vector space structure because most of the statistical models are never clear the vector space. Of course, those are not the Hilbert spaces. But as long as you now see how to generalize this theorem in terms of the K divergence with the zero sectional curvatures, it somehow makes sense, right? So that's why we just want to first know how to verify whether or not certain statistical models are having the zero sectional curvature. Okay? That corresponds to the Gaussian curvature equal to 0. That's the very first step. So once you check how to check certain statistical models has a zero curvature, then you can just proceed this algorithm. So the algorithm is indeed just the applied side, whereas the understanding of the geometric, the behind structure, is somehow really deep, so that you can play both of them. So let me today finish just here, but just one thing. So I intend to write down small letter EM algorithm, but there's also capital EM, usually called by the expectation maximization algorithm. Those are almost equivalent, but not exactly. And the difference is coming from the so-called base rule in the statistical world. So I might mention that as in the last seminar, and then it's just simply much the same. So now you can see somehow so it's quite geometric, right? But if you just look at this theorem from the statistical context, then you might just think, it's just some messy the statement. But this is purely somehow geometric statement, right? Yeah, just the same. So I do not know how many times we still have for the seminar, maybe 1 or 2 times.
So this is week 8 we're in, so probably week 9 and week 10, so 2 more times.
Got it. So yeah, I just want to say 2 things. So number 1, so I will just proceed this manner about the explanation of the EM algorithm for sure. But for the undergraduate students, I highly recommend you to proceed the calculation of the sectional curvature. Okay? So now you see why I put emphasis on the calculating sectional curvature, because without it, you have no intuition how to choose certain statistical models here, right? So those selection are coming from the calculation of the certain curvature with respect to certain connection. So what I at least force you to do is with respect to Leibniz with a connection from the Riemannian geometry. So you can just use the just very known formula of the sectional curvature so that at least you can check the values explicit. Then you can just move on here, and then you can just try to interpret the geometry like the picture in the applied towards the applied way. So that's somewhat fancy. And if you want to keep learning this subject, then I will definitely open next quarter. Hopefully, I might so busy, but we'll see. Okay, yeah, that's it for today. Yeah, let me know if you have any questions.
So what will be the application of the EM algorithm?
Just search Google. So tons of algorithms. I like applications. Okay, many directions: finance, machine learning, optical transport, statistics. Yeah, tons of applications indeed. Yeah, and so even later, if you are serious to learn the CS, the AI direction, so mostly the cost function is written in terms of the KL divergence and try to minimize this quantity. So the most of the algorithm in the applied mathematics is just a look at the KL divergence and minimize each slot repeatedly. But now you have certain geometric understanding. So this is not like the coincidence from just based on the heuristics. Of course, the reality of doing research is just based on the heuristics with the messy data, but for sure, but this somehow gives them geometric intuition. And so which I like it.
So I'm a little bit confused at some point with the relationship, because it seemed we were using KL divergence as our metric, but now in the probability distribution stage we use the Fisher information metric as our distance metric. So I think I got lost somewhere about the connection between those.
So today what I mentioned is, so as long as you want to write down the expectation of two, in fact, random vectors. So this was what I wrote is this guy. This makes sense with respect to the Hilbert space structure, okay? So in some sense, what you can see, so if you look at this expression, for example, this expression only makes sense with the choice of the probability, either the mass function or probability density function. You agree? So then let me just mention this choice of this P over here is a P, meaning the expectation with respect to this probability mass function. You agree? So once you change the probability, like the density or the probability mass function here, that will change this quantity. You agree? So if I now draw the space of the probability mass function, okay? So if I just choose one single the element over here, so let me say this is P. Can you see? We indeed make the inner product, right? This is the inner product. So that what we essentially did is that we just make the tangent space. And with respect to this point, we just create the inner product with the chosen point. Then as long as we have inner product, we can just quantify all geometrical quantities, right? And this was the way to define the notion of the Fisher metric. So that when you just now compare the definition of the Fisher metric, this is exactly the same with this guy. Meaning that, so as long as we have a series like the expression, then we are able to write down in some sense as a Riemann integral function, right? So if you now go back to look at the definition of the Fisher metric, this is exactly the same. So this is not coincidence that with respect to the Fisher metric, this is now perpendicular of those two trajectories. It's indeed actually the same expression from here, to be honest. Now you can just compare. But now this is somehow the interesting procedure so that you can now compare. One is from the Hilbert space structure, but now we do not have the Hilbert space structure any longer, but still you can actually do something, right? So now you can see how actually advanced to appreciate this type of the picture. So even with the Hilbert space structure, it's quite indeed advanced. This is a graduate level in some sense. But in order to appreciate the algorithm in terms of the KL divergence, you need to know the knowledge of the somehow the manifold or the surfaces and the curvatures, right? So without it, you cannot appreciate this picture somehow properly, right? So you should know the notion of the either the Riemann metric or the inner product of each tangent spaces, right? And what I said is if you just compare, so you can just look at the note today from our website, and you can see this expression is in the same with the Fisher metric. So we are not actually saying something different. We are indeed saying something the same. The inner product is the same, but we are just now working the set which is
where does the KL divergence?
Sorry?
How does it relate to this specifically?
That's a good point. So now let's just go back to the very first example today we mentioned. What is this? Do you agree this is just nothing but a dot product? Is it clear? So I just write down the notion of the dot product in terms of the identity matrix. So now let me just use distance squared from the distance from the origin to the given vector x. So what is this expression? This expression nothing but this guy, or just a magnitude square. Just a silly expression. But that what you can see is that if you choose the Hessian from the center here, so the Hessian just means we take all second order derivatives, agree? For each ij component, ij entries, right? So when you take the second order derivative here, what happens? Agree?
Yeah.
So that I can simply divide by 1/2 to recover this guy. So the identity matrix here is coming from the Hessian of the distance square, okay? And according to the third seminar, I just provide the formula in the note, is that what we learned is that if you now look at the K divergence between P theta and P theta hat, okay? And I evaluate, so this theta hat is fixed. So in the statistics, this is usually called by the true distribution, okay? But the notion is not important. We fix as a theta hat, and we evaluate this K divergence when theta is equal to theta hat for the Hessian. Okay, I should actually say 1/2. Okay, so you can just read my note, and once you just grab this expression, what do you guess? You will get Fisher information metric at the true parameter. This is what you can check from the third note we saw. So that we replace the notion of the distance square.
I see. So when we want to use the distance function of the probability distribution, we're talking about KL.
Yeah, we are talking about the KL as the replacement of the distance square on the space of the probability distributions or the probability density functions. So that indeed we view the KL divergence as a distance square in a sense that in order to recover the Riemannian metric, so the Riemannian metric is coming from the Hessian matrix of the distance square, but we can use the KL divergence to recover the desired Riemannian metric. So that we replace distance square by the KL divergence and look at the Pythagorean theorem here. So that you indeed look just view this as a distance square. So that we indeed make such like the figure with the 90 degree with respect to the Fisher metric, then you can take the geodesics. That still is the same Pythagorean relation.
So my question here is, because when I was trying to compute sectional curvature last week, like this idea of when I was looking on resources online, this idea of geodesics came up, but I wasn't able to. I'm having trouble seeing the connection behind everything like that. So you say this is related to the fact that you need the sectional curvature to be 0.
So the trajectory here, these statistical like the submodels are either the mixture family or the exponential family. They satisfy the sectional curvature equal to 0 with respect to the so-called the pair of the certain connection. In fact, those are not the Levi-Civita connection, rigorously speaking, but still you are able to find a certain connection that makes the sectional curvature equal to 0 for both of them. So the making the Pythagorean theorem is seeking the statistical models have somehow the 0 curvature. Today I just want to address it somehow naively. So, but is it clear? So that this is sort of the way to generalize the Pythagorean theorem in the case of Hilbert space, but not exactly the vector space structure. So there's some distortion, so that the connection is any longer the Levi-Civita connection in the Riemannian geometry sense. But still, this theorem is astonishing. So yeah, let me know if you have any other comments or questions. So I want undergrad students to appreciate this type of the picture in the following sense. So you might consider your career to like the build with the applied direction, with the like the high salary in the big tech or whatsoever. But as long as you like to use the knowledge of the mathematical major, so this is one of the possible like the direction. So that one like the understanding or the interpretation is purely like the advanced level of the geometry, right? But the other side is the purely somehow heuristics, so that you just need to minimize the K divergence as cost functions. But now you have a geometry understanding and interpretation out of it, so that you can study both of them. So it might be beneficial for your career. So that's the part you might consider. But the drawback is that in order to really do the research in this direction, there are tons of things that you need to learn, like the Riemannian geometry, the kind of things, right? So that's why I first want you to learn how to calculate the sectional curvature. then you can appreciate this type of picture more somehow precisely. Is it clear? So that's why I so far just avoid to mention this theorem, because I first wanted to focus on calculating the section curvature in the beginning. So then now you see why we actually really need it, because we are not now working on the Hilbert space any longer. But the Hilbert space is also one of the most important like the object in the applied direction, but this application is not. So certain statistical like the context, so this is also quite influential, I should say. So the learning this subject is so-called the information geometry. Okay. So I think this direction is also one of the promising direction for the next generation, in my personal opinion. So because this requires the advanced knowledge in the pure mathematics, but at the same time, it has like the huge like the influence like the algorithms, because it's quite simple in some sense. And those like the families are also quite influential in some sense, so that you can actually do lots of things for your future. Okay, so if any of you want to like present the calculation of section curvature, I am welcome you to join to do some silly calculation on the board, right? For your own learning. I will not record your calculation if you do not want it, but yeah, so this is always the way to learn the Riemannian geometry. First, just calculate the section curvature in terms of calculus and linear algebra, and then just try to see what was really going on. Okay, not just reading that book and the theorems. Yeah, that's all for today. So we will meet maybe next week, right?
Thank you.